a useful analytical technique to measure different, or to look at mixtures of liquids, okay? Particularly volatile liquids that don't decompose under high heat. So what we're going to end up doing is just like TLC, which was thin layer chromatography, except now it's going to be done in the gas phase. So to control that gas phase, we're going to end up putting it inside a new piece of equipment, and that's going to be our gas chromatography instrument, for lack of a better description. Okay? So it's a nice little magic box, and it does all sorts of fancy stuff for us. Okay? It is extremely sensitive. It can detect very small amounts of compounds, so it's nice for that reason. Just like with TLC, you end up with two phases, and you're partitioning between those two phases. So you get your mobile phase and your stationary phase. Your mobile phase, in this case, because we're looking at the gas phase, is an inert gas. So the most common gas or carrier gas used is helium. You might see some other ones in there as well. For our instrument, because it's more expensive to deal with helium, and it's also more expensive to deal with that equipment, our little mobile units use natural air instead of helium, okay, as the carrier gas. So our units have a compressor built into them that will siphon air from the outside the box and pump it into the instrument, okay, and push our compound along. We've also got stationary phases inside that. We're going to have a very small column inside the little black box that you don't get to see. And that stationary phase is usually a high boiling liquid that's put inside of it. Okay, so you're usually looking at a very thin column with that stationary phase on it. So if we go ahead and take a look at a picture. So if we had a fancier piece of equipment, this is probably more along the lines of what it would look like. Okay? So we've got the injection port, which is where your sample will get injected. You'll be using a very, very small needle, which is fragile as well, so make sure you're careful with that. You'll inject that into a rubber septum, which keeps all the other gases out and allows us to just inject what we want. That's going to get directly injected into the column. The column is attached to the carrier gas. So your carrier gas, in this case, is an external tank, which we don't have. So our system just has a little inlet, and it starts pumping air in over the top of your sample. Okay? So the air gets pushed through the sample, and our compound gets pushed through the column. Okay? To speed up this process, we'll also have our column run through an oven. The whole intent of the oven is to keep things hot, or in the gas phase, or at least partitioning between the gas phase and the liquid phase. When it's in the gas phase, it tends to move faster, so it'll come out of the column earlier. When it's in the liquid phase, it runs slower because, well, it's a liquid, not a gas. Okay? So the ovens typically in GCs are very, very controlled environments. It's not like your oven at home or even your hot plates, okay? Because you don't control those very well. You can turn them on, but then temperature fluctuates all over the place. The ovens inside the GC fluctuate within fractions of degrees. So ours will record temperatures up to, the 10th of a decimal place, 10th of a degree. Okay, so they're fairly accurate in what they're actually portraying. The column itself, like I said already, is packed with some stationary phase. It's typically a mix between a liquid phase and a solid phase. That solid phase is there just to maximize surface area, and the liquid phase is what's actually grabbing a hold of your compounds. It can be a non-volatile liquid, usually a wax or some kind of high boiling hydrocarbon. Okay? So nothing particularly exciting there. As the compound passes through the column, eventually it reaches the detector. There are a variety of different detectors out there. In most cases, what they are is just a wall that detects a change in electric current. So when a compound happens to impact that surface, the electric current changes. The instrument converts that change in electric current into an amount, okay, or a number of things hitting it. And what we end up seeing on the recorder is what we've got here, where you get peaks. So in this case, the one shown on that computer screen has 2 peaks. Okay, so there are 2 compounds in that sample. So then it comes down to the different settings that we can use. Our instrument has a whole bunch of different ones. Typically, these are all figured out for you, and in fact, for our lab, they are figured out for you. So I spent this weekend going through and trying to decide which conditions actually work best to separate your compounds in a reasonable amount of time. Okay? So here are the variety of settings that we can run through. We can change the start temperature. So as soon as we inject the compound, what temperature does our mixture see right away? Okay, we can then adjust the hold time, which means how long do we stay at that individual temperature. Okay, the longer we stay at that temperature, the more or less separation we'll see. We can then look at a ramp rate. So if we wanted to change our temperature through the course of our GC experiment, we could then adjust that by picking a final temperature and including a ramp rate. How fast does our sample actually heat to that point? Okay? And then we got a hold time. How long are we going to leave it at that high temperature? The total length, we won't change directly. If you change that number, you're ultimately changing the second hold time. Okay? And then finally, the pressure, how much air is actually pumped into the sample. So what's the maximum pressure you're putting in, all that kind of fun stuff. When you change each of these variables, you'll change the ability of your compound to separate, or your mixture to separate within the column. Okay? As far as figuring out how to do it, it's pretty much guess and check. You go through and adjust to see what things change, what things don't change. How does GC end up separating? It's largely based on boiling point, okay, or intermolecular forces, polarity. Okay? They're all very related, and depending on the different temperatures, you may end up separating more based on boiling point than on intermolecular forces. That can also change depending on the solid substrate or the stationary phase that you end up using. Okay? As far as we're concerned, they're going to separate based on boiling points. Okay? So if we have a very low boiling point compound, that means the intermolecular forces are very, very weak. Okay? So primarily, it doesn't stick to the stationary phase. Well, if it doesn't stick to the stationary phase, what's it going to do? Nice, easy answer. What's the opposite of stationary? Mobile phase. So it's going to start to move. Okay? So that would be based on its polarity. If we provided enough heat, okay, so if we got rid of the intermolecular force effect by providing enough heat to cause our compound to move into the gas phase, it's now in the gas phase, which is in our mobile phase, and it will also travel a lot faster. Okay? So lower boiling points and lower polarity compounds typically travel very, very fast through the column. Okay? The higher the boiling point and the higher the polarity, the slower it takes, or the longer it takes to get through. So what we can go through and do now that we understand what the basic principles are and how it separates, we can start to tweak the instrument settings. Okay? So this just happened to be the second condition that I attempted. So I went through and reported the start temp, the hold time, ramp rate, final temperature, all that fun stuff. Okay? The mixture that I added into this had 6 compounds in it. How many peaks do you see? 4. So are these conditions a good set of conditions for the experiment? No, we don't see all 6 peaks, so that doesn't work. So we're going to want to change our conditions. What condition should we change? So there's 2 things that we could change. We could change our start temp or our pressure. Anything else probably isn't going to help. If we change the final temp, is that really going to matter? Okay, our compounds all came out really, really early on, okay, within 2 minutes, and our final temp is the same as our start temp. So if we upped our final temp, that's not going to help us out. And we don't want to cool things down. If anything, we want to heat during the process to speed things through it. If we cool things down, we're going to get all sorts of weird slowing effects. Okay? So we could change the start temp. What would we do to the start temperature? Should we increase it? We increase the start temperature. Let's say make it 120 degrees. What have we provided more of to our compounds? Temperature is a measure of energy. What are we supplying more to our compound? More energy. What happens if we have more energy? Probably stop falling asleep. I don't blame you. I didn't say that. Okay. What happens if we have more energy? We move more, which means we would expect our compounds to move faster through the column. So increasing the temperature is not a good idea. Okay. We want our compounds to slow down, take a little bit longer to get through the column. Ideally then we could see it separate. So we could drop our start temperature. What about the pressure? I know we don't have any units on that, but the pressure is kilopascals. Should we increase the pressure or decrease the pressure? If we increase, what does that mean? That means we're pushing more gas. So what we want to do is decrease the pressure. There's less compound or less carrier gas pushing across our compounds, which means we would expect our compounds to travel a little bit slower, which makes sense. We want our compounds to spend a little bit more time on the column so they can separate. So we moved, in this case, to the third condition. Pretty much, I think the only thing I changed, actually, was the pressure. Okay. Does this work as a possible condition? Nope. We still only see 4 peaks. We get better separation. So by reducing the pressure, that did help us out. Okay, but it's not getting us those 6 peaks that we want to see. So we'll change it yet again. In this case, we'll change the temperature. So I dropped the temperature by 20 degrees. Okay. How many peaks do we see now? 5. So we've increased the number of signals that we're seeing, which is good, but we're still 1 short. Okay. Any ideas where that 1 short one is? It's kind of hard to decide at this point. Okay. It could be hidden within that last peak. Our last compound could be embedded in with that one, or it could be somewhere out here, okay, off the scale. So what could we do to our conditions to change them so that we could potentially see our 6th peak?
Make the time longer.
So we could expand the time, okay, which in a situation where we had tons of time, that's not a bad option, except we don't have a ton of time. We've got roughly 10 groups per room, or at least that's what I'm allowing for. If each of you take 5 minutes, we're pushing half the class time, assuming no mistakes are made and you perfectly run your sample every single time. Okay. That's not very likely, so expanding our total time is probably not going to be the best option. So what should we do instead? We'll adjust our temperature. Okay. In this case, what we're going to do is drop our start temperature. Okay. Drop the start temperature, and I also dropped the pressure. Tried to maintain the 4-minute time zone so that we could at least get through the experiment as fast as we possibly could. And these conditions seem to work best. Unfortunately for you, and we're working on it, my note-taking ability was not the greatest, and I'm not positive that these are the correct conditions. So we are currently testing it to make sure that these conditions are appropriate so that you can see all possible 6 compounds. Okay? Those final conditions will get adjusted in the posted Blackboard background packet, and I will also have those printed out and put with the GC instrument so that you know exactly what conditions you should be using for your experiment. Okay? Why do we want to pick all the exact same conditions? See you for next slide. Any ideas? What happens if I change the conditions? What happened to my signals? Let's say this compound, let's not do that. Let's say this was the 6th compound, that peak. What happened when I changed the conditions? Where's that last peak in condition 3? Probably there, right? Did it show up at the exact same time? No, it's slightly different. How about in condition 6? It's even more different. Okay? If we change the conditions, we change the time it takes for our compound to come off. Okay? Okay, so we could go through and count each individual signal and say, yes, there were 6 things there, or there's 2 things there, or there's 3. Okay, but that's all we'd be able to get out of it. So what we can do is run a standard mixture of all the known compounds. Okay, and if you run the exact same conditions as your standard, what would we expect for the retention time for, say, that 6th compound? It should be exactly the same. So not only can we identify how many compounds are in the mixture, we can identify what compound it was. Okay? And we'll do that by looking at the retention times. It's all based on their boiling point and how they interact with the stationary phase and the mobile phase. If it's the same compound, we would expect it to interact in the exact same fashion, okay, giving us the exact same result. So what you'll end up calculating is a retention time. Okay? Very, very similar to TLC, okay, and your RF values, except it's going to be a lot easier. Calculate the retention time for me, if you will, for, come on, pencil, that peak. What's the retention time for that compound? That's not a very nice one for me to pick. Let's try that again. How about that compound? Come on, eraser. 2 3/4. How do you know that? What are you eyeballing? The time running along the x-axis, right? Really, really difficult, okay? In the older pieces of equipment, you had to do a comparison between all sorts of weird things and conversion factors. One of the things that's nice about technology and the current technology that we have is all you have to do is read the graph. Wherever that peak is, that's your retention time. You're measuring from that very tippy top of that signal, okay, which I can't draw perfectly there. Okay? That gives you the retention time for that individual compound. Nice and straightforward. Okay? So, retention times for these compounds. What do you get for A? What do you say, 2? Compound A? That's a squiggly line, not a 2, by the way. Say about 1.5 minutes. That looks reasonable. How about compound B? Okay, 4 minutes. Compound C? Just for you guys. Okay. Which compound has the highest boiling point?
C.
How do we know it's C?
It's the tallest.
No.
The longest amount of time.
Took the longest amount of time to get out of the column. We haven't looked at the intensity of that signal yet. All we've looked at is how much time it takes for that signal to show up. Okay? So the compound that has the highest boiling point will take the longest to get off the column. Okay? The compound that has the lowest boiling point take the shortest amount of time to get off the column, right? Okay? So we can go through and rank compounds, determine things based on that. Okay? Particularly if you know the boiling points of your compounds. The morning did this really fast, so let's see what you guys do. Arrange the following ketones according to the order that they come off the column, first to last. Which one's going to come off first? YD. Lowest boiling point. Which is second? Y. Second lowest boiling point. Which one's third? Dare I ask why? Okay, and then 4, right? Okay. Might as well. The very last thing that we'll talk about here is quantitative analysis, which is looking at the intensity of that signal, or the intensity of the peak. Depending on the instrument and how it detects, what we can do is relate the size or the intensity of our peak to the other peaks to determine relative amounts. Okay? So we'd need to figure out how much an individual peak represented. And if we look back at examples, let's see. get an example. If we looked at just intensity here, does that really give us an idea purely of the amount of compound there? Okay, why did the signal start to go up in here? What did the instrument detect at that point? Compound, which is why the peak went up. Okay, which is why we'd have to take into consideration all of that area. And we'd have to compare that to all of this area and to all of that area. So we can't do just a direct one-for-one height relationship. We have to look at the area underneath the curve. Okay? How do we go about doing that? I know everybody loves calculus. We want to take an integration. We want to integrate our data to figure out the area underneath the curve. Okay? Again, one of the nice fancy things about technology is our computers will do it for us. Okay? And the software will do it for us as well. So what you'll end up doing is taking your data, and this is not going to be the nicest looking drawing, but I'm going to attempt to draw it. So if we've got your data, and you've got, say, a signal here and a signal here, what you can go through and do is select that data first. So you can use the mouse and you can just click and kind of drag, and you'll see this whole area get shaded in. Okay? At that point, we want to tell the computer to integrate that data. There's a button up at the very, very top. I really wanted to get a picture of this so that I didn't have to draw this, but it didn't work. You'll have a little button, which is now really zoomed in. It'll show you a picture of your data. And then it, not even positive this is right, but I think it's close. Shows something along these lines. Okay, which is saying integration. Okay, Robin knows what the button is. Stephanie knows what the button is. They will help you find that button. Okay, so all you've got to do is click that, and that will integrate that peak. You need to get the integral for all of the peaks. So what you'll end up doing after you integrate the first one, you'll go back to your data, click and select around the next peak, and the next peak, and the next peak, and so on until you get all of them